Welcome back to Q Point. Today we discuss the non-inverting amplifier. This is the circuit diagram of a non-inverting amplifier. The input is applied at the non-inverting terminal and the feedback is still negative from output to the inverting terminal. Amplifiers generally employ negative feedback. Now by virtual ground we have Vp equal to Vn, and since Vp is equal to Vi, Vn also must be equal to Vi. So because of virtual ground, this voltage is Vi. Now since we know this voltage at N, you can apply KCL at the node N. The current leaving must be equal to the current entering. So the result of application of KCL will be Vi by R1 equal to Vo minus Vi by R2. Simplifying and taking the ratio Vo by Vi, we get this is equal to 1 plus R2 by R1. The gain is positive, that is why we call this as a non-inverting amplifier, and you can note that the gain is always greater than 1 plus a positive quantity. Now we have derived an expression for the gain of a non-inverting amplifier with an operational amplifier whose open loop gain is infinity. Only because the open loop gain is infinity, we can say that Vp equal to Vn. Assume that the gain is not infinity, it is finite. Open loop gain is finite. And the other parameters are ideal, that is the input resistance is infinity and the output resistance is 0. So what is the effect of that finite open loop gain on the amplifier performance? So we can now express the differential inputs Vd equal to Vp minus Vn, and it is equal to Vo by A, where A is finite. And since Vp equal to Vi, this expression becomes Vi minus Vn equal to Vo by A. So you can find Vn. Vn is equal to Vi minus Vo by A. Now that we know the voltage at the node N, we can apply KCL at this node as before. So the current leaving the node must be equal to current entering. We have Vi minus Vo by A by R1, that is the current leaving. This is equal to Vo minus Vi minus Vo by A by R2. Now simplify this expression to get the final expression. So we will simplify this. We can write this expression as Vo minus Vi minus Vo by A into 1 by R1 plus 1 by R2 equal to Vo by R2. You take the collect Vi minus Vo by A from both sides and take it outside the bracket. What you get is 1 by R1 plus 1 by R2 equal to Vo by R. And we know R1, 1 by R1 plus 1 by R2 is equal to R1 plus R2 divided by R1 R2. Employing that rule, this is Vi minus Vo by A into R1 plus R2 by R1 R2 equal to Vo by R2. Now this term R1 plus R2 by R1 is equal to 1 plus R2 by R1. So if you take R2 outside the bracket, what is inside the bracket is 1 plus R2 by R1. So our expression now becomes Vi minus Vo by A by R2 into 1 plus R2 by R1 equal to Vo by R2. Now our aim is to find Vo by Vi, so collect the terms of Vo together and Vi together and take the ratio Vo by Vi. We can cancel out R2 on both sides and this expression becomes Vo into 1 plus R2 by R1 by A equal to Vi into 1 plus R2 by R1. Simplifying, you get the expression for gain as 1 plus R2 by R1 by 1 plus R2 by R1 by A. Now compare this expression with that of the inverting case. For the inverting amplifier, we already have defined or discussed the effect of finite open loop gain. There, you can comparing these two equations, you can see that the denominator in both the cases is the same. It is because both the amplifiers use the same feedback path. And the numerator is 1 plus R2 by R1 is the ideal gain of this amplifier, this non-inverting amplifier. And in the inverting amplifier case, we have the numerator as minus R2 by R1, which was the ideal gain of the inverting amplifier. So you can see that the numerator is the ideal gain of the amplifier, and the denominator is 1 plus R2 by R1 by A. 1 plus R2 by R1 by A, it is divided by A, the gain. And if A is infinity, the denominator becomes 1, so that the expression tends to 1 plus R2 by R1, which is the ideal gain of non-inverting amplifier. Now, in the expression for the gain of an ideal non-inverting amplifier, you have seen that the expression is 1 plus R2 by R1. Now assume that R1 is equal to infinity. R1 is an open circuit. Then the gain becomes unity irrespective of the value of R2. So if R1 is an open circuit, you can make R2 any value. So let us consider or construct an amplifier with R2 equal to 0 and R1 is equal to infinity, an open circuit. R1 is open and R2 is 0. So from this expression, the gain is equal to 1. So Vi is equal to Vo, or we say that the output follows the input, and so it is called a voltage follower. The gain of the voltage, the input resistance of the voltage follower is infinity as in the previous case, and the output resistance is 0 because this is an ideal operational amplifier. The main application of this is as a buffer or an impedance transformer. Signal from a very high impedance is transformed into a very low impedance. Both the signals are equal, but the outside the impedance is 0 and the input side the impedance is infinity. So the signal is transformed from a high impedance to a low impedance. That is what is known as an impedance transformation. The non-inverting summer, an application of a non-inverting amplifier. We already have discussed the inverting summer or the weighted summer. Similar to that, here assume that you have three voltage sources V1, V2 and V3 connected to the non-inverting terminal of the amplifier through resistors R1, R2, R3. In the inverting case, we have written V1 by R1 plus V2 by R2 plus V3 by R3 is the current or the total current. Here that is not possible because this lead is not at virtual ground. So seeing such a circuit diagram, your first tendency is to write V1 by R1 plus V2 by R2 plus V3 by R3 is equal to I, which is equal to 0. I is equal to 0 in this case. This expression is wrong since the non-inverting terminal is not at virtual ground. This is an important point. The non-inverting terminal is not at virtual ground and the non-inverting terminal cannot act as a summing point. So what you have to do is you have to apply the principle of superposition, find Vp corresponding to V1 alone with V2 and V3 short-circuited or connected to ground. Similarly, find Vp with V2 alone and V3 alone, and finally sum all these values. That will be equal to Vp, and that is the input. That multiplied by 1 plus Rf by Ra will be the output. So we will write or apply superposition theorem to find Vp. You cannot directly write V1 plus V1 by R1 plus V2 by R2 plus V3 by R3 equal to 0. That is wrong. Because when you are writing V1 by R1 plus V2 by R2 plus V3 by R3, all these three currents are entering this node and no current is leaving. That is not possible. That means that some charges will be accumulated at this point. Kirchhoff's current law states that the total current entering a node must leave the node. The total current entering the node must be equal to the total current leaving. So that principle is not applicable here. So let us find Vp by applying the principle of superposition. First, find the voltage at P due to V1 alone, short circuiting V2 and V3. Then find the voltage at Vp with V2 alone, short circuiting V1 and V3. Then find Vp due to V3 alone, short circuiting V1 and V2. And finally add all these voltages. That is what we have to do. So first we will consider Vp1. Vp1 is the voltage at Vp because of V1 alone acting. The other two sources are shorted. The other two terminals are grounded. So by this circuit diagram you can see that V1, there is a current, of course. That current cannot take this path. So that current is passing through these two resistors. And you can see that R2 and R3 are in parallel. So what will be the voltage at this point? By potential divider rule, it is V1 into this value divided by the sum of resistances. Sum of R1 plus R2 parallel R3. So we can write the expression like this. Vp1 is the voltage at P due to V1 alone. That is a notation that we are using here. V1 into R2 parallel R3 divided by R1 plus R2 parallel R3. This is the expression. We use the simple potential divider rule here. Now we will simplify this expression. This is equal to V1 into the parallel combination of R2 and R3 will be R2 R3 by R2 plus R3. And this is R1 plus R2 R3 by R2 plus R3. So it's only an algebraic manipulation. I am not explaining all this. These are the steps given. You can verify these steps. Now the R2 plus R3 terms in denominators can be cancelled, resulting in this expression. Now look at this expression. If there is a term R1 also in the numerator, R1 R2 R3 by R1 R2 plus R2 R3 plus R3 R1, then it would have been the parallel combination of the three resistors R1, R2 and R3. So in order to make that, multiply and divide by R1. So what you get is a parallel combination of three resistors plus an additional term 1 by R1. So you get V1 is equal to R1 parallel R2 parallel R3 divided by R1. Let us denote the R1 parallel R2 parallel R3 by a single term, say Vp. Then Vp1, the value of Vp because of the source V1 alone acting is equal to Rp divided by R1 into V1, where Rp is the parallel combination of the three resistors. R1 parallel, effective value of R1 parallel R2 parallel R3. Similarly, finding Vp2 and Vp3, we get Vp2 equal to Rp by R2 into V2 and Vp3 equal to Rp by R3 into V3. So Vp will be equal to, that is the voltage at the non-inverting terminal or the input of the amplifier will be equal to Vp1 plus Vp2 plus Vp3, which is equal to Rp by R1 V1 plus Rp by R2 V2 plus Rp by R3 V3. And this is the input. The output will be input multiplied by the gain. The gain is 1 plus Rf by Ra. So the output is equal to 1 plus Rf by Ra into Vp, where Vp is given by this expression Rp by R1 V1 plus Rp by R2 V2 plus Rp by R3 V3. So you are substituting for that. We get an expression for Vo equals 1 plus Rf by Ra into Rp by R1 V1 plus Rp by R2 V2 plus Rp by R3 V3. So as in the inverting case, here also you can find that this is proportional to the weighted sum of inputs. V1 is weighted by Rp by R1, where Rp is the effective value of parallel combination of three resistors. Similarly, V2 is weighted by Rp by R2, V3 is weighted by Rp by R3. If there are in general n voltage sources and n resistances, still the expression has the same form, Rp by R1 V1 plus Rp by R2 V2 plus etc plus Rp by Rn Vn, where now Rp is the parallel combination of all the n resistors, effective value of the parallel combination of the n resistors. So this is the expression for output in this case. So you can treat this also as a weighted summer, and you can see that the sum is not inverted, it is positive. So this is a non-inverting summer. Now consider some special cases. If R2 equal to R1 equal to R2 equal to R3, all the three resistors are equal, say R, then Rp, the parallel combination of three equal resistors, R3 equal to R by 3. So our expression for output now becomes VO equal to 1 plus RF by RA into V1 plus V2 plus V3 by 3. V1 plus V2 plus V3 by 3 is the average of the three inputs. So you can see that the output is proportional to the average of the three inputs, or the average of the three inputs multiplied by the gain of the amplifier. Now what will happen if 1 plus RF by RA is equal to 3? Or if the gain of the amplifier is chosen to be equal to the number of inputs, 3 is the number of inputs here. If 1 plus RF by RA is equal to the number of inputs, then this 3 will be cancelling out. So we will be getting VO equal to V1 plus V2 plus V3. The output is the sum of inputs. If there are n sources connected here, take 1 plus RF by RA equal to n. Choose RF and RA such that 1 plus RF by RA is equal to n. In that case, you will be getting the output is equal to V1 plus V2 plus V3. See, the input resistance and output resistance are the same. Input resistance is infinity and output resistance is 0. So this is a non-inverting summer. Let us consider some examples. Example 1. You have an operational amplifier and a PNP transistor connected like this. What is the voltage across RL? This is a question. See, assume that the operational amplifier is ideal, because nothing of ideality or non-ideality is mentioned in the question. Assume that the operational amplifier is ideal. And since the operational amplifier is ideal, the voltage at the non-inverting terminal also must be equal to 10 volt. So the voltage at this point must be equal to 10. So you have a resistor Re with a 15 volt connected to one lead and a 10 volt connected to the other lead. So the potential difference is 5 volts, and so the current through Re is equal to 5 milliamperes. The same current should flow through this resistance RL, because no current can flow to the input of the operational amplifier. So there is a current of 5 milliampere flowing through the resistance RL, which will develop a voltage across it 5 milliamperes into 100 ohm, which is equal to 0.5 volt. Now consider another example. Determine the gain VO by VI for the circuit given below. The operational amplifier is given to be ideal. We have seen a similar problem in the inverting case, but here you can see that these resistors are 2R and these two resistors are R. So the resistors are fitted in a specific ratio. Again, we start by finding the voltage at the inverting terminal, which will be equal to Vi. So because of virtual ground, Vn is equal to Vi. So we can calculate I1, and I1 must be equal to I2. I2 is equal to I1. So Vi by R must be equal to the current through R, 2R also. So I1 is equal to Vi by R. I2 is equal to I1, also equal to Vi by R. So the current through this resistor also is equal to Vi by R. What is the next step? Find the voltage at this point. So once we know the voltage at this point and we know the current through this resistance, the voltage at this point Q must be equal to the voltage Vi plus the voltage across the 2R resistance. So Vq is equal to I2 into 2R by Vi plus Vi, and I2 is equal to Vi by R. So this is Vi by R into 2R. So we have 2 Vi plus Vi is equal to 3 Vi. So the voltage at this point is equal to 3 times the voltage at the non-inverting term, the inverting terminal. And once we know the voltage at this point, you can calculate I3. I3 is equal to voltage at this point divided by R. So finding I3, I3 equal to VQ divided by R. And now substitute VQ. VQ is equal to 3 Vi. So this is 3 Vi by R. And we know Vi by R is equal to I1. Or we can write this as Vi by R is equal to I2 equal to I1. So you can write I3 as, say, using this relationship, you can write this as 3I2. I3 is equal to 3 times I2. Now what remains is to find I4. Applying KCL at this node Q. I4 is the current entering and I2 and I3 are leaving. So I4 must be equal to I2 plus I3. Substitute all these values. So we get I4. I3 is equal to 3I2. I2 is equal to Vi by R. So substituting, what you get is 3I2. Okay, 3I2 plus I2 is equal to 4I2. I4 is equal to 4I2, which is equal to 4 Vi by R. Now VO is the voltage at this point, or the voltage at Q. This is the direction in which the current is flowing. The voltage at Q plus the voltage across the 2R resistance will be equal to VO. So it is I4 into 2R plus VQ. Now substitute I4. I4 is equal to 4 Vi by R. 4 Vi by R into 2R. And VQ is 3 Vi. So it is 4 into Vi by R into 2R plus 3 Vi. R and R cancels. So this is 8 Vi plus 3 Vi, which is equal to 11 Vi. So we have VO is equal to 11 Vi, or VO by Vi is equal to 11. So you can see that the gain is constant. If you take ratios, resistors in this ratio, you can see that the gain is fixed, the output is fixed. See, if you use R is equal to 10K, connected 10K here, and you do 20Ks here, the gain is equal to 11. Now consider another example. For the circuit given, find the ideal closed loop gain and B, the actual closed loop gain if the open loop gain is 150,000. There are two values. You are asked to find a closed loop gain in two cases. In one case, the gain to be ideal, so that A is open loop gain is infinity, and in the second case, the open loop gain is given to be 150,000. Find the closed loop gain. So in the first case, of course, there is no current flowing through this resistance, so there is no voltage drop across this. So whatever Vi is applied here is available at Vp. So there is no drop here since there is no current flow. So Vi is equal to Vp or Vp equal to Vi and Vp equal to Vn. So Vi is available here. Vi is shorted to the output. So the output also is Vi. So the gain is equal to 1. Now in the second case, open loop gain is given to be 150,000. We will apply that conditions Vd equal to Vp minus Vn and Vn is equal to Vi. This is equal to Vo divided by A. A is 150,000. Since Vp equal to Vi, Vn equal to Vi minus Vo by A. We have seen this expression earlier. So the output Vn is shorted to Vo. Since Vn is equal to Vi minus Vo by A, the output also must be equal to Vi minus Vo by A. So we have an expression Vo equal to Vi minus Vo by A. Collecting terms on Vo together, we get Vo into 1 plus 1 by A is equal to Vi, or Vo by Vi is equal to 1 by 1 plus 1 by A. Substituting this, 1 by 1 plus 150,000, which is equal to 0.999, etc. So you can see that even if the gain is finite, since the gain is very high, the open loop gain is very high, the output is almost equal to 1, or the gain is almost equal to 1. Now consider another example. In the figure, the op-amp is given to be ideal. Determine I1 in terms of Vi. I1 is the resistance and the current flowing through the resistance R1. And 2, let R1 equal to 9 kilo ohm and RL equal to 1 kilo ohm. If the op-amp saturates at plus or minus 10 volt, find the maximum value of Vi and I1 before the op-amp saturates. Let us take the first case. In the first case, again, given the operational amplifier is given to be ideal, so Vi must be equal to the voltage at the non-inverting terminal, and the voltage at the inverting terminal is shorted to this point. So the voltage at this point must be equal to Vi. These are what we know. Vn is equal to Vi. The output voltage VL equal to Vn equal to Vi. So the voltage at this point also is equal to Vi. So what will be the current through RL? Current through RL will be equal to Vi by RL, because VL is equal to Vi. So the current through RL is equal to VL divided by RL. And that is the current flowing through this resistance, and that current should be equal to I1, because there is no current possible to the input of the operational amplifier. So I1 also is equal to Vi. So this is Vi by RL, and I1 also is equal to Vi by RL. This is the first part. I1 in terms of Vi. The current I1 is equal to Vi divided by RL. Now for the second part, R1 equal to 9 kilo ohms and RL is equal to 1 kilo. If the op-amp saturates at plus or minus 10 volt, that means if you are giving an input voltage so that the output, the gain of the amplifier in such a way that the output is greater than the power supply is connected. See, for example, suppose the operational amplifier in this case is powered at plus and minus 10 volt, plus 10 volt and minus 10 volt. Then the maximum output or maximum undistorted output possible from the operational amplifier is 10 volt. If you set up the amplifier in such a way that the output happens to be greater than 10 volt, the output will be clipped off at the 10 volt level. Or we say that the operational amplifier saturates. So here it is given that the operational amplifier saturates at plus or minus 10 volt, positive side and negative side. That means the operational amplifier is supplied with a plus or minus 10 volt supply. So the maximum output voltage possible from the operational amplifier is equal to 10 volt. So you can say VO is the output voltage of the operational amplifier, VL is the voltage across the resistance RL, and because of this VO and VL difference, this current is flowing. So you can write I1 is equal to VO minus VL divided by R1, which is equal to VO minus VI divided by R1. This implies that VO equal to VI plus I1 R1. VO, the voltage amplifier, output of the operational amplifier is equal to VI plus I1 R1. The voltage at this point plus I1 R1. Given VO to be a maximum value of VO is 10 volt. So you can write 10 is equal to VI plus I1 R1. So we can manipulate this equation like this. Our aim is to find what is the maximum input possible. So VI is equal to 10 minus I1 R1 equal to 10 minus I1 is V1 by RL into R1. So this is substituting R1 is equal to 9 kilo ohms and RL equal to 1 kilo ohm. This is 10 minus 9 VI. So VI is equal to 10 minus 9 VI, which means 10 VI is equal to 10 or VI is equal to 1 volt. The maximum value of input voltage you can apply or maximum magnitude of, if it is a sine wave or an alternating waveform, the maximum amplitude of that waveform that you can apply is 1 volt. If it is greater than 1 volt, the output saturates. Now we have to find I1 also. We can substitute in this expression. So I1 is equal to 10 minus VI by R1. VI is given to be 1 volt. We have calculated that. So this is 10 minus 1 divided by R1 is 9 into 10 raised to 3, which is equal to 1 mA. Now these are the references. And thank you. We'll meet again with another lecture.